this video will look at different types of processor. So CPUs, the way in which they are created, the way in which they are put together, their architecture has changed over the years, and it's done that in order to improve efficiency and effectiveness. So we will look at the difference between two different architectures, the von Neumann architecture and the Harvard, and also contemporary architectures. We'll look at multi-core and parallel systems, and we'll have a look also at complex instruction set computing and reduced instruction set computing processors. And also a little bit about graphical processing units as well, and how they differ from CPUs. Okay, so von Neumann, Harvard and contemporary architectures. Now in GCSE you would have learnt about the von Neumann architecture. It is used in pretty much the majority of computers these days. And what is important to recognize about the von Neumann architecture is that the instructions and data for a given program are stored together in memory. And each instruction and data item uses the same data bus to get to the CPU. And here's an example or a diagram, to show that. So you've got the RAM where the instructions and data are stored together, and they use the data bus to send data to the CPU. They use the same data bus. Now with Harvard architecture, this is less common, but it's used in specialist and embedded systems. With the Harvard architecture, it differs in that the data and instructions are actually stored separately in memory. And the instructions have got their own data bus, and the data's got its own data bus. So there are at least two data buses that are being made use of. So you've got your CPU, you've got your RAM. Now a part of the RAM is dedicated just to data, and it's got its own data bus to send data to the CPU. And the instructions have got its own part of the RAM, and again its own data bus to send the instructions to the CPU. So in terms of the advantages and disadvantages, with the von Neumann architecture, advantages are that you've got one data bus, so it's less complex for the control unit to sort of oversee what's going on in the CPU. So it's much easier for the control unit to manage that. One data bus means that it's cheaper to manufacture von Neumann architecture. And also, probably the most important is that the memory can be used really efficiently. So all the memory can be used for either instructions or data. You don't waste any memory at all. You can fill it all up with either instructions or data. But a big disadvantage to the von Neumann architecture is that it can only process or fetch an instruction or data at one time. It's got one data bus, so it will fetch a bit of instruction, or it might fetch data, but it can't do can't do that simultaneously. It can't get data and instructions simultaneously at the same time. So with the Harvard architecture, a big advantage is kind of the opposite of what I just said. Because there's two data buses, it means that because that data and the instructions, they're separated in memory, it means that a piece of data and an instruction can actually be fetched at the same time. They can be fetched simultaneously, and that can improve performance. A disadvantage, though, is that because the architecture is a little bit more complex in that there's two data buses, it means that it's a little bit more expensive. It takes a little bit longer to manufacture. Also, because you're separating the data and instructions in the RAM, it means that the memory is not used as efficiently. So memory can be wasted, as free instruction memory cannot be used for programs data, and vice versa. Okay, contemporary architectures. So modern day processors, they still do use the von Neumann architecture. It's very, very widely used. It is, after all, cheaper to manufacture. It makes more efficient use of RAM. Data instructions can be stored together. So yeah, you're not wasting that space in RAM, so it's much more efficient. However, lots of modern processors will also make use of the Harvard architecture in their cache. So they might divide the cache memory into separate parts, separating the data and instructions, and therefore taking the advantage of the parallel processing, so that you can actually fetch them in data, fetch some instructions at the same time. So modern architectures may well sort of marry together both the von Neumann and Harvard architecture ideas. Okay, so CPUs nowadays, when it comes to their instruction sets, they may well either be use complex instruction sets or reduced instruction sets. So an instruction set, remember, is just a list of instructions that the control unit can understand and can perform on the data. But like I said, different CPUs may use one of two types of instruction set. So the complex instruction set and reduced instruction set, RISC and RISC. So we'll look at what they are and what their advantages and disadvantages are. Okay, so first of all, with RISC processors, they will have a large amount of known instructions. They might have sort of 80 to 100 different instructions that the control unit can carry out, and they will be complex in nature. Now, what we mean by that is that each instruction might represent lots of steps, several steps. So if you think of a single instruction, which might be to multiply two numbers together, in a RISC processor, that single instruction will come bundled with lots of different steps. So RISC processors, if you think about the idea of coming bundled with lots of different steps, when you multiply two numbers, we have to first of all, or the CPU will first of all have to load those values, then multiply them, and then actually store the results. So when we're talking about multiplying two numbers, we will still need to load those values, we'll still need to store those results as well. And in a RISC processor, the multiply instruction will have that load and store operation automatically automated within that instruction. Okay, and it might take several clock cycles to complete. So you might have to load number one, load number two, multiply number one and two together, and then store the results. So quite a few clock cycles probably being used there, but for one instruction, which is just to multiply. So the complex instruction set will incorporate all of those extra little things that have to go on, like loading and storing, and it'll automate them. So because a complex instruction set is known to the CPU, it's easier for a compiler to convert a high-level language multiply statement into the appropriate assembly language instructions. It just needs to convert it over, and because the CPU knows that a multiply, you would need to actually load the value and also store the result as well as multiplying, it can be converted quite easily. And because it's just one instruction, although it might represent lots of different steps, because it's just one instruction, it will require little memory to actually be stored. Now, reduced instruction set computing processors, they will have far fewer instructions, maybe 30 to 40. So for example, although there may be an instruction to multiply two numbers, just like there was in the RISC instruction set, in the reduced instruction set CPU, the multiply instruction will literally just represent the multiplication part. It won't automatically load those values, it won't automatically store them. So in RISC processors, the instructions, they're not complex, they're simple. They just carry out a single operation. They don't automate all the other required steps, such as load and store. So as a result, RISC processors, more instructions are needed to actually perform the task. So here on the left hand side, you can see how in that red box, that represents the multiply instruction, whereby load and store are all part of that instruction in the complex instruction set. Whereas with the RISC processor, you can see that the instruction to multiply is given in this red box, and that is just a single simple instruction. It doesn't come bundled with having to load numbers or store the result. So more simple instructions are required to perform the operation. So what you really need to recognize is that if you multiply with complex or if a RISC processor multiplies, it will use, let's just make it simple here, 1, 2, 3, 4 different operations, 4 clock cycles To do the same thing with the reduced instruction set, it would be, again, I'm oversimplifying here, but 1, 2, 3, 4 operations, so 4 clock cycles. You're probably thinking, what's the point? What's the difference? Why, they're still having to do the same amount of operations. It's still going to take the same amount of time. So what benefit would one or the other actually bring? Okay, so let's have a look at this. The RISC processor, it might look a little bit more limited, but it actually has a huge advantage over RISC processors. So because each one is simple and each one takes a single clock cycle, and because they're all separated, it means that actually a RISC processor can benefit from pipelining. So whereby as one instruction is being executed, the next one can be decoded and the next one can be fetched, and that can happen all at the same time. RISC processors, their instructions, remember they're complex. You would have to fully execute the entire multiplication instruction, whereby you'd have to load the values, multiply them and store the results. You'd have to do all of that before you could fetch the next one. They're all bundled together, remember. So they're all bundled, you fetch them, you decode, you execute them, and then you move on to the next instruction. Whereas with RISC, because they're all separated, they can actually be queued up, and pipelining can provide the benefit in terms of speed. So as a result, RISC instructions will execute at least as fast as RISC. So again, from this example, I've oversimplified it, but let's say 4 clock cycles for each. But actually, if you think about the idea that although they're 4 clock cycles, if you could actually queue those up in the RISC processor, then you can actually gain some benefits over time. So, advantages of the complex instruction computing processor. Because a complex instruction, so for example multiply, is known to the CPU, it is easier for a compiler to convert a high-level language multiply statement into the appropriate assembly language. And because it's just one instruction, which might represent several steps, it requires less memory to be stored. The disadvantage, though, is that each of these RISC instructions have to be fully executed before the next one can be fetched, so it can't really benefit from pipelining. On the other hand, RISC processors, that's their biggest advantage. Because each instruction is simple, each one takes a single clock cycle to be executed, which means that we can actually queue them up. We can benefit from pipelining. So an instruction can be executed whilst another one's being decoded, whilst the other one's being fetched, all at the same time, all simultaneously. A disadvantage, though, of RISC processors is that a single instruction won't automate all the other steps required. It won't know to load and store. That needs to be done separately. So that obviously when your high-level code is being compiled, that would need to be taken care of. And as a result, in RISC, more instructions are required to perform a task. Okay, multi-core and parallel systems. So other characteristics of modern day processors is that they might not just have a single core. They might have 2 cores, they might have quad cores, they might have multiple cores. So multi-core processors have more than one processing unit, and in theory, and it's important to recognize that, in theory, they can carry out multiple jobs at once. So this principle of carrying out lots of different jobs all at the same time is known as parallel processing, and it means that more processes can be executed over the same time period. But remember, as I said in the previous video, a major issue with this is that software has to be written to specifically allow multiple jobs to be carried out at the same time. So as many older pieces of software aren't written to make use of this technology, multi-core and parallel systems do have limitations. They may, even if they had, let's say, 8 cores, if they're only running one bit of software which isn't being designed for that particular architecture, then you wouldn't get any of the benefits. Okay, graphical processing units. So these aren't CPUs, these are GPUs. So they are separate, they are different. Now, if you think about parallel processing, GPUs are amazing at parallel processing. They're amazing at carrying out loads and loads of jobs at the same time, simultaneously. So a GPU is a graphics processing unit, and it's traditionally just been responsible for processing loads and loads of data, visual data, graphical data, really, really quickly. And the way it does that is by having hundreds and hundreds and hundreds of cores. Okay, so whereas a CPU might have a single core, 2 cores, 4 cores, 8 cores, it might be really good, CPUs of course, at processing lots of different data in lots of different ways. A graphical processing unit is very good at processing lots and lots of data all at the same time, but it might be limited in the actual instructions it can carry out. Nevertheless, it's very good at handling lots and lots of processes at once. So GPUs, they're often in separate cards, you add them to the system, or they could be embedded on motherboards. But either way, they're actually known as co-processors, so they provide extra processing support for the CPU. They do that by taking some of the intensive jobs that the CPU might have to do and free it up so the CPU can do lots of different jobs, make the computer work really effectively. So it might sort of take a little bit of pressure off the CPU. So whereas a multi-core CPU can carry out various instructions on different data in parallel, a GPU is designed to carry out one instruction on multiple pieces of data in parallel. So think about that again. CPUs can carry out lots of different instructions on different data in parallel, whereas a GPU can carry out one instruction on hundreds of bits of data all at the same time. So as a result, software engineers, they've taken advantage of this, and now lots of non-graphic related jobs can be carried out by the GPU. Things like machine learning, whereby it might just be 1 or 2 instructions that need to be carried out over and over again on thousands of bits of data. That can be carried out by the GPU. So machine learning is one application, modern day application of GPU processor. Modeling and cryptocurrency mining. So any job where it's just the same thing over and over again on multiple bits of data, that might be best pushed out towards a GPU.